Hello everyone. So in today's video, we are going to go over this paper, Pre-train, Prompt and Predict, a systematic survey of prompting methods in NLP. So you can see this is a survey paper and this is quite a long paper, around 30 pages excluding the references. So maybe I'll break this into parts and then combine them and upload them into one video, or I'll just see how it goes. So this paper is by Liu et al. So the authors are from Carnegie Mellon, National University of Singapore, uh, only these two universities. So let's just go over the abstract. I thought this paper would be relevant because we are in the golden age of prompting, as some would say. A lot of papers are just focused on finding the right prompts, and there are lots of methods now. So this paper surveys and organizes research work in a new paradigm, which is prompt-based learning. So unlike traditional supervised learning, which trains a model to take in input X and predict Y, prompt-based learning is based on language models that predict the probability of text directly. That model the probability of text directly. So to use these models to perform prediction, the original input X is modified using a template into a textual string prompt X dash that has some unfilled slots, and then the language model is used to probabilistically fill the unfilled information to obtain a final string X hat from which the final output Y can be derived. So you create some slots, the model fills those slots, and then you use that to get your output. For instance, you have this example. So the first one, JDK is developed by, and you have this empty slot, and the answer is Oracle. Then you have this super long text, and you ask the model to give you a TLDR. So the model outputs a summary, which is BART. The first task was done by BERT, which is an MLM, which is trained on an MLM objective. Then you have Birds Can Fly, which is just Ernie. I'm not sure if Ernie is a model or uh, not. So this framework is powerful and attractive for a number of reasons. It allows the language model to be pre-trained on massive amounts of raw text, and by defining a new prompting function, the model is able to perform few shot or even zero shot learning, adapting to new scenarios with few or no labeled data. In this paper, they introduce the basics of this promising paradigm, describe a unified set of mathematical notation that can cover a wide variety of existing work, and organize existing work along several dimensions. So the choice of pre-trained model, prompts, and tuning strategies. To make the field more accessible to interested beginners, we not only make a systematic review of existing works and a highly structured typology of prompt-based concepts, but also release other resources. So our website NLPedia Pre-train, which is continuously being updated. All right, so this is just abstract. I hope you get the idea of what prompting is and uh, what we'll go over now. So there have been lots of favors. You can just go over this one page long content. So in index page. So you have the formal description, the pre-trained language models, then prompt engineering, answer engineering, multi-prompt learning. So training strategies for prompt methods, then you have some applications, prompt relevant topics, the challenges, and then some meta-analysis followed by conclusion and appendix. So let's just delve right into it. So two C's changes in NLP. So you have fully supervised learning, where a task-specific model is trained solely on a dataset of input-output examples for the target task, and this has played a central role in many ML tasks. So because such fully supervised datasets are ever insufficient for learning high quality models, early NLP models relied heavily on feature engineering. So prior to the era of deep learning, where NLP researchers or engineers use their domain knowledge to define and extract salient features from raw text and provide models with the appropriate inductive bias to learn from this data. So with the advent of neural network models for NLP, salient features were learned jointly with the training of the model itself, and hence focus shifted to architecture engineering, where the inductive bias was rather provided through the design of a suitable network architecture conducive to learning such features. So in deep learning models, what you have is you have this black box, you give it the input and you get the output, and you hope or you hypothesize that your model learns to extract relevant features and does not learn spurious correlations, but we all know that is far from the truth. These models heavily rely on spurious correlation in many cases. So, however, from 2017 to 2019, there was a sea change in the learning of NLP models, and this fully supervised paradigm is now playing an ever shrinking role. Specifically, the standard shifted to the pre train and fine tune paradigm. So, in this paradigm, a model with fixed architecture is pre trained as a language model, predicting the probability of observed textual data because the raw textual data is necessary, uh, available in abundance. And then these language models train a large data set, learn some general purpose features of the language and its modeling. So they learn what language is, how is it structured, and so on. So this is encoded in the model parameters. Then they are adapted to different downstream tasks by introducing additional parameters and fine-tuning them using task-specific objective function. So within this paradigm, the focus turned mainly to objective engineering, so designing the training objective used at both pre-training and fine-tuning stages. So this would be like how you would give in the input, what loss you would use, how would the input pass through the network, and so on. So for example, Zhang et al. Show that introducing a loss function of predicting salient sentences from a document will lead to a better pre-trained model for text summarization. Notably, the main body of the pre-trained LM is generally, but not always, fine-tuned as well to make it more suitable for solving the downstream tasks. So you can either freeze your pre-trained model or just leave it as is. So now, as of this writing in 2021, we are in the middle of the second sea change, in which pre-trained fine-tuned procedure is replaced by one in which we dub pre-train, prompt, and predict. In this paradigm, instead of adapting pre-trained language models via objective engineering, downstream tasks, and so on, via objective engineering, sorry, downstream tasks are formulated to look more like those solved during the original language model training with the help of a textual prompt. So, for example, when recognizing the emotion of a social media post, like this is your post, I missed the bus today, we will continue with the prompt, I felt so, and then a blank. And the language model is asked to fill the blank with an emotion bearing word. Or if we choose the prompt English, I missed the bus today, and then give it uh, like just in the same structural format as we had English, we add French. Then we want the model to realize, okay, we are asking for a translation, and the language model may be able to fill in the blanks with a French translation. In this way, by selecting the appropriate prompts, we can manipulate the model behavior so that the pre-trained language model itself can be used to predict the desired output, sometimes even without any additional task-specific training. So the advantage of this method is that given a suite of appropriate prompts, a single language model trained in an entirely unsupervised fashion can be used to solve a great number of tasks. However, as with most commonly enticing prospects, there is a catch. This method introduces the necessity for prompt engineering, so finding the most appropriate prompt to allow a language model to solve the task at hand. So this might seem all too good to be true, right? And this is your bottleneck right here, finding the right prompts. And this is not a trivial task. These examples might make it seem trivial. Okay, for a sentiment task I'll do this, for a uh, machine translation task I'll do this. But what if your prompt doesn't work? There is no really good way to debug it, right? You just need to try. This survey attempts to organize the current state of the knowledge in this rapidly developing field by providing an overview and formal definition of prompting methods and an overview of the pre-trained language models that use these prompts. So this is followed by in-depth discussion of prompting methods from basics such as prompt engineering and answer engineering to more advanced concepts such as multi-prompt learning methods and prompt-aware training methods. So we'll just go over these as we reach those sections. We then organize the various applications to which prompt-based learning methods have been applied and discuss how they interact with the choice of prompting method. Finally, we attempt to situate the current state of prompting methods in the research ecosystem, making connections to other research fields, suggesting some current challenging problems, and performing a meta analysis. Finally, in order to help beginners who are interested in this field more effectively, we highlight some systematic resources about prompt learning. So, you have a website of prompt learning that contains frequent updates to the survey. And then, what's figure one? So, figure one was just this figure that I reckon this figure that we saw in the start is figure one. Or am I wrong? Figure one. I don't see any figure 1, so I'm assuming that was figure 1. Right, so there's this table, the four paradigms in NLP. You have those fully supervised learning, oh, sorry, where you do not have neural networks yet. So you have language models, you have uh, these, so you have these relationship between tasks, they are isolated, and then you have extracting these features. Then you got these fully supervised learning networks where you had the architecture and uh, you had to focus on what architecture you were using. Still, they are isolated. Then you got into the pre-trained fine-tune regime. So you have these new objectives which you were now looking into, and then your language model got connected into these tasks. So tagging, classification, and generation. If I'm not wrong, yeah, tagging, classification, and generation. And then in this final regime, now they are all connected, but the arrows are directed in the opposite direction. So this means that the task to LM denotes you are now adapting the downstream task during for towards the language model. So you are adapting your task to be similar to how language models were trained. So a formal description of prompting in supervised learning in NLP. In a traditional supervised learning system for NLP, we take in an input X, usually text, and predict an output Y based on a model which maximizes the probability, which learns to maximize the probability of the correct output. So in order to learn the parameters theta, we use a dataset containing pairs of input-output and train a model to predict this conditional probability. So for example, you have text analysis, which takes in an input X and predicts a label Y from a fixed set of labels. To give an example, you have sentiment analysis. So I love this movie and predict the label positive out of these sets. So plus plus meaning highly positive, I guess, in this set. Second, you have conditional text generation task, which takes in input X and generates another text Y. So you have this translation task from Finnish to English. Now, the basics of prompting. The main issue with supervised learning is that in order to train a model, it is necessary to have supervised data for the task, which cannot be found in large amounts for many tasks, and you need large amount of data to say train a transformer. Prompt-based learning methods for NLP attempt to circumvent this issue by instead learning an LM that models the probability of x given theta. So you are of the unsupervised. This is an unsupervised setting, right? Because you no longer need the labels. You just have text, and you are maximizing the probability of text, and then using this probability to predict y, reducing or obviating the need for large supervised features. So how is this predicting y? You would fill in a blank, and that blank you'll finally extract the output to get y. Like in the example we saw earlier where oracle was being predicted, and then you can just extract the token predicted. So in this section they lay down the mathematical description of the most fundamental form of prompting, which encompasses many works on prompting and can expand to cover others as well. Specifically, basic prompting predicts the highest scoring y hat in 3 steps, y cap in 3 steps. Okay, so we'll go over this table when this is referred, because I feel we need some context before we go over this. Now the first stage is prompt addition. In this step, a prompting function is applied to modify the input into a prompt x prime. So in the majority of previous work, this consists of a two-step process. You apply a template, which is a textual string that has two slots, an input and an answer slot, and then for an intermediate generated answer text Z that will later be mapped into Y. So this answer slot is mapped into the input, and then you fill the slot with the input text. So in the case of sentiment analysis, I love this movie. The template may be X. Overall, it was a Z movie, and then you fill in X. So X dash would become I love this movie. Overall, all it was a Z movie, and then in a case of machine translation, it might be something like this. Notably, the prompts above will have an empty slot to fill in Z either in the middle or at the end. In the following text, we will refer to the first variety of prompt with a slot to fill in the middle of the text as a close prompt. So these are important words. And the second variety as a prefix prompt. So you might have read in several places that BERT is trained over close prompts. In many cases, these template words are not necessarily composed of natural language. They could be virtual words. So example represented by numeric IDs, which would be embedded in a continuous space later. So those prompts are not necessarily strings; they can just be embeddings which are added to your embedding. And some prompting methods even generate continuous vectors directly. So they are, I believe, called soft prompting methods. The number of X slots and the number of Z slot can be flexibly changed for the need of task at hand. So if you have multiple hierarchical classification, I guess, then you can have something else and so on. Then you have the answer search. So next we search for the highest scoring Z cap that maximizes the score of the language model. So first we define Z as a set of permissible values for Z. Z could range from the entirety of the language vocabulary, so in the case of generative tasks, or a small subset in the case of classification, such as defining Z to be these words. And then you take the words with the highest probability. So these words are used to represent these particular classes, these particular symbols. Then you have this function which is going to do the filling that fills in the location Z in prompt X prime with the potential answer Z. We will call any prompt that has gone through this process as a filled prompt. Particularly, if the prompt is filled with a true answer, we will refer to as an answered prompt. Finally, we search over the set of potential answers Z by calculating the probability of the corresponding filled prompts using a pre-trained language model. So this is just taking in the checking the model's output, getting the model outputs a probability distribution over the entire vocabulary space, right? Then you check out of these five words which has the highest probability in that distribution. The search function could be an argmax search that searches for the highest scoring output, or sampling that randomly generates outputs following the probability distributions of the language model. Finally, you have answer mapping. So answer mapping, so you don't need Z cap, right? You want Y cap. So this is trivial in many cases. You just look back, find a blank which you were supposed to fill, extract the output. So this is where the answer is the output itself, as in the case of natural language generation tasks such as translation. But there are cases where multiple answers could be result in the same out. For example, one may use multiple different sentiment bearing words, excellent, fabulous, wonderful, to represent a single class, in which case it is necessary to have a mapping between the searched answer and the output value. So just to clarify, this right here, this search function can do this in multiple ways. You can just get the argmax, say, over the predicted vocabulary, a vector with dimensions of vocab, and suppose that is uh, say you get the word happy, then you look back into your prompt. But then again, you might not have a mapping which has all those words. So one other way would be the method which I was proposing earlier. You just check among excellent, good, okay, bad, and horrible in the probability distribution which word has the highest probability. So these are multiple heuristics. I reckon we've gone over this. So let's have a look at the table now. So you have input, you have the output, then you have this prompting function, then you get the prompt where you fill in the input into the X location, then you fill the prompt, and then you have an answered prompt where the answered prompt would be the true answer, while the filled prompt is filled with any answer, and then you extract the answer. So this would be the token that filled in that cell. So just to remind you, the models are not perfect. They would, of course, in many places fill in the wrong answer as well. So now you have the design considerations for prompting. So now that we have a basic mathematical formulation, we elaborate a few of the basic design considerations that go into a prompting method. So now you have the pre-trained model, which is also really important. So there are a wide variety of pre-trained language models that could be used to calculate probability of X given theta. In section 3, we give a primer specifically from the dimension that are important for interpreting this work. All right. Then prompt engineering, given that the prompt specifies the task choosing a proper prompt has a large effect not only on accuracy but also on which task the model performs in the first place. So if you give it a prompt for sentiment analysis, you can't really expect it to do translation, right? Then for answer engineering, depending on the task, we may want to design Z differently, possibly along with the mapping function. So it fills in the word, but you then need to extract it back. Expanding the paradigm as stated above, the above equations represent only the simplest of the various underlying frameworks that have been proposed to do this variety of prompting. So in section 6, we discuss ways to expand this underlying paradigm to further improve the results of applicability. And then you have prompt-based training strategies. So these are methods to train parameters either of the prompt, the language model, or both. Right. So going over this table is just the different prompting methods based on the different tasks. Um, so for pre-trained language models, you have these. For prompt engineering, you have these prompts, and you have for answer engineering, and I guess we'll go over these as the work goes on because I guess not everyone is familiar with every specific task, right? But everyone has some basic idea about how different tasks in NLP are done. So example of input template and answer for different tasks. So this table just shows some examples. So in the type column, you have what type of task it is, and then you in the task column, you have what exact task it is, and then you have the input template and answers, probable answers. So for instance, for text classification, you might have sentiment, topic, and intention. You have this input, you create these templates, and then you get these outputs. Then for text span classification, you have these kinds of aspect sentiment based tasks. Then for text pair classification, you have this is natural language inference. For tagging, you have named entity recognition. For text generation, you have summarization as well as translation. So these are some of the popular tasks along these axes. Then for pre-trained language models, you have given the impact that pre-trained language models have had on NLP in the pre-trained and fine-tuned paradigm. There are already a number of high-quality surveys that have been done. Nonetheless, in this chapter, we present a systematic view of various pre-trained language models, which organize them along various axes in a more systematic way, particularly focus on aspects salient to prompting method. Below, we'll detail them through the lens of main training objective, type of text noising, auxiliary objective, attention mass, typical architecture, and preferred application scenarios. So for training objectives, you have the standard language modeling objectives. Uh, okay, so the main objective of a pre-trained language model almost invariably consists of some sort of objective predicting the probability of text X. So standard language model objectives do precisely this, training the model to optimize the probability P of X of text from a training corpus. In these cases, the text is generally predicted in an autoregressive fashion, predicting the tokens in a sequence one at a time. This is usually done from left to right as detailed below because our languages are left to right, right? A popular alternative to standard LM objectives are denoising objectives, which apply some noising function to the input, and then we try to predict the original input sentence given this noise input. And even for noising, we have some two common flavors. So you have corrupted text reconstruction. So in this, the objective restores the process text to its uncorrupted state by calculating loss over only the noised parts of the input, while full text reconstruction. In these objectives, the text is reconstructed by calculating the loss over the entirety of the input text, whether it has been noised or not. So I guess this makes sense, right? So just to make it a bit more clear, if you have this sentence and you noise these two parts, so in the case of corrupted text reconstruction, you would only fix this, but in the case of full text reconstruction, you would take all of this in and create back the output. So the main training objective of the pre-trained language models plays an important role in determining its applicability to particular prompting tasks. For example, left to right autoregressive LMs may be suitable for prefix prompts, whereas reconstruction objective may be more suitable for close prompts. So I guess this is also quite intuitive because for prefix prompts, you For left to right autoregressive language models, it takes leverages the entire input on one side on the left of the current uh, token you're standing on. So a prefix prompt would have all that, but in closed style prompts for reconstruction objectives, you could just noise any word in between. So I guess this part is pretty clear. In addition, models trained with standard LM and FTR objectives may be more suitable for tasks regarding text generation, whereas classification can be formulated using models trained with any of these objectives. So in addition to the main training objective above, a number of auxiliary objectives have been engineered to further improve models' ability to perform certain types of tasks. So some commonly used objectives are present in auxiliary in the appendix. All right. So then you have noising functions and training objectives based on reconstruction. You noise the input, right? So how do you noise that? So to obtain the noise text x cap, uh, the noising function has an effect on the efficacy of the learning algorithm. If you do very simple noising, it would not learn much. If you do very complex noising, it wouldn't learn anything again because it won't be able to denoise it. In addition, prior knowledge can be incorporated by controlling the type of noise. So noise could focus on entities, which allow us to learn a model which focuses on entities. So for instance, you have the masking operation, which would mask some tokens. Then you have replace, which would replace them. Then you have delete, which would delete them. Then you have permute, which would rotate them, which would jumble them in a random order. Then you have rotate, which would just shuffle the words. And then you have concatenate, which would concatenate different languages. For masking, you have the most common example, Devlin et al., which is a BERT paper. The text that has been masked in different levels, replacing a token or multiple tokens with a special token such as mask. Notably, masking can either be random from some distribution or specifically designed to introduce some prior knowledge, so masking entities. Replacement by Raffel et al. So in this, you replace the tokens, so except in it is similar to masking except that the token or multi-token span is not replaced with mask but with another token or piece of information. So for deletion, tokens or multi-tokens will be deleted without the addition of mask or any other token, and this is usually uh, together used in the FTR loss because it would reconstruct everything. For permutation, the text is divided into different spans, token, subsent, subsentential spans or sentences, and then these spans can be permuted into a new text. Finally, the directionality also matters. So language models can be left to right. So in the case of left to right, the representation of good in the sentence, this is a good movie, would be calculated based only on the previous word. So this is a. The variety of factorization is particularly widely used. This variety of factorization is particularly widely used as standard LM objective or when calculating the output of a FTR objective. Because in full text reconstruction, you would construct it one step at a time. In bidirectional ones, for the above example, good would be influenced by all words, even the following word movie. So in addition to these two common directionalities, it is possible to mix the two strategies together in a single model or perform conditioning of the representation in a random permuted order. So I think this Yang et al. Paper is your ExcelNet paper. Please don't quote me on that, but I think so. Notably, when implementing these strategies within a neural model, the conditioning is generally implemented through attention masking. This conditioning is implemented through attention masking, which masks out the values in an attentional model, such as the popular transformer architecture. So the words you don't want to see, you give them a zero attention weight. So in full, you allow everything. In diagonal, this is like predicting x. For x1, you only have x1. For x1, x2, you have these two. So basically, a shaded box at ij indicates that the attention mechanism is allowed to attend to the input element I at the output time step j. Then for mixture, you allow both of them. So some typical pre-training methods, left to right language models. So these are L2RLM, which is a variety of language model predicting the upcoming word or assign a probability P of X to a sequence of words. So this probability is commonly broken down in the chain rule in a left to right fashion. So basically, For a sentence x1, x2, so you have first the probability of x, then you condition the probability of x2 on x, and so on. So this is a left to right language model. Then you have masked language models where everything is connected. For prefix language models, some parts are connected totally, but some are not. And then you have an encoder decoder simple setup where first you have an encoder, and the encoder is hidden states of encoder are connected to the decoder. So examples and applicable scenario. Left to right language models have been standard since the proposal by Markov in 1913, which I believe he's the guy behind Markov chains, and have been used continuously since then in both count-based and neural forms. Representative examples of modern pre-trained left to right LMs are GPT-3 and GPT-Neo. L2R pre-trained language models are also the popular backbone that many prompting methods adopt. One practical reason for this is that many models are large and ponderous to train or not even av- available publicly. Thus, using these models in the pre-train and fine-tune regimen is often not possible. So these are used for prompting because you can't really fine-tune them, right? So you just prompt them and get the outputs. Um, right. So I think I'll be stopping here, and then I'll continue from here on. Okay, I'll just finish this section then. For we've covered till here. So this shows the typical architecture for pre-trained language models. So you have what happens with the input, what happens with the output, and what are the applications. So I guess this is already covered in what we've seen so far. Then you have MLMs, mass language models. So while autoregressive models provide powerful tools for modeling the probability of text, they also have disadvantages such as requiring representations be calculated from left to right when the focus is shifted to generating the optimal representation for downstream tasks such as classification. Many other options become possible and often preferable. One popular bidirectional objective used widely is the masked language model or the MLM, so such as BERT, which aims to predict masked text pieces based on the surrounding context. So you predict xi based on x1 to xi minus 1 and then xi plus 1 to xn. And then some applicable scenario, BERT, Ernie. Okay, Ernie is a model, so I was wrong. And in prompting methods, MLMs are generally more suitable for natural language understanding or analysis tasks like classification, inference, and extractive Q&A. These tasks are often relatively easy to be reformulated into closed problems, which are consistent with the training objective of the MLM, which was mass language filling. Additionally, MLMs have been a pre-trained model of choice when exploring methods that combine prompting with fine-tuning. And finally, you have prefix encoder decoder for conditional text generation, such as translation and summarization, where the input is given and the goal is to generate output. We need a pre-trained model that is both capable of encoding and generating text. There are two popular architectures for this purpose, which share a common thread of using an encoder with a fully connected mask to encode the source, and then the target Y is generated auto-regressively. So for the prefix language model, which is a left to right language model that decodes Y condition on a prefix sequence X, which is encoded by the same model parameters but with a fully connected mask. So you want a representation to leverage everything and not just process it into a left to right fashion. So notably, this encourages the prefix LM to learn a better representation of the input. So a corrupted text reconstruction objective is usually applied over X, so it gives it more power to learn by denoising. In the encoder decoder framework, then the model uses a left to right LM to encode Y, so to decode Y conditioned on a separate encoder for text, which is a fully connected mask. The parameters are not shared, however. However, in the above prefix language model, the parameters were shared. Similarly, you could also noise it. So prefix LMs have been explored in UniLM, Ernie, and other encoder-decoder models are widely used in the pre-trained models such as T5, BART, and MAS. So in uh, this is the difference between, I guess, T5 and things like Ernie. In T5 BART, you have separate encoder-decoders, while Ernie has one shared parameters. Pre-trained models with prefix LMs and encoder-decoder paradigms can be naturally used to generate text representation tasks or without prompting using input text. However, recent studies reveal that other non-generative tasks such as information extraction, question answering, and text generation evaluation can be reformulated as generation problems by providing appropriate prompts. Therefore, prompting methods broaden the applicability of these generation-oriented pre-trained models. For example, pre-trained models like BART are less used in NER, while prompting methods make BART applicable and breaks the difficulty of unified modeling among different tasks. So earlier uh, you had a different model for everything, but now you don't really need a different model to do everything. So I hope I'm not going too fast. I was assuming you have a bit ideas of what pre-training, deep learning, and all that stuff is, and you're just exploring prompting with me. Of course, I'm also exploring prompting. So thank you guys for tuning in. This is part one, and I'll upload the part two as soon as I record it. So hope to see you again next time as well. So hello everyone. Let's continue from where we left off last time. So we had finished the first three sections. The third section just discussed about the different types of models on which prompting is used. So it is sort of a survey on current pre-trained language models, but from the perspective of prompting. So let's now have a look at prompt engineering. So prompt engineering is the process of creating a prompting function, which we discussed earlier, that recalls in the most effective uh, that results in the most effective performance on the downstream task. So in many previous works, this has involved prompt template engineering, like we saw in the case of sentiment analysis, where a human engineer or algorithm searches for best template. As shown in the prompt engineering section of figure 1, one must consider the prompt shape and then decide whether to take a manual or automated approach to create prompts. So the prompt shape, as noted above, there are two main varieties of prompt. You have closed prompts, which are fill in the blanks of textual strings, and prefix prompts, which continue a string prefix. Which one is chosen will depend both on the task and the model that is being used to solve the task, right? So, for instance, if you want to have trained the model on fill in the blank type tasks, then you of course use closed prompts. In general, for the tasks regarding generation or tasks being solved using standard autoregressive language models, prefix prompts tend to be more conducive, and as they mesh really well with the left to right nature of the model, because once you see all the context on the left, then you start making predictions. For tasks that are solved using mass language models, closed prompts are a good fit, as they can closely match the form of the pre-training task. So full text reconstructions model are more versatile, and they can be used with either close or prefix prompts. Finally, for some tasks regarding multiple inputs such as text pair classification, prompt templates must contain space for two inputs or more. So if you have more input samples. Then template engineering. Perhaps the most natural way to create prompts is to manually create intuitive templates based on human introspection. For example, the seminal Llama dataset provides manually created closed templates to probe knowledge in language models. Brown et al. Create manually crafted prefix prompts to handle a wide variety of tasks, including question answering, translation, and probing tasks for common sense reasoning. Then Schick and Schutz 2020 and 2021 A and B use predefined templates in a few short learning setting on text classification and conditional text generation. So manual template, an example would be uh, you have the sentence X and then you add I thought it was, and then you add a blank Z. So X would get filled in by your input, and this is for sentiment analysis. So if this is say for movie reviews, X might be I really liked that movie and I thought it was, and then it would get filled in. Then automated template learning. While the strategy of manually crafting templates is intuitive and does allow solving various tasks with some degree of accuracy, there are several issues with this approach. Crafting and experimenting with these prompts is an art. Oh, sorry. Creating and experimenting with these prompts is an art. that takes time and experience, and for complicated tasks like semantic parsing, and even experienced prompt designers may fail to manually discover optimal prompts. To address these problems, a number of methods have been proposed to automate template design. In particular, automatically induced prompts can further separate into discrete prompts where the prompt is actual text string, and continuous prompt where the prompt is instead described directly in the embedding space of the underlying language model. So one other orthogonal design consideration is whether the prompting function is static or not. So does it give the same output for the same prompt, or dynamic where it generates a custom template for each input? Sorry, by static they mean that does it give the same prompt template for each input, or dynamic where it generates custom templates for each input? Both static and dynamic strategies have been used for different varieties of discrete and continuous prompt, as uh, will be discussed below. So let's have a look at discrete prompts first. So I hope you understand what discrete prompts are. Discrete prompts are, as we saw earlier, prompts which are actually text. So like the one I wrote here, a soft prompt would be, or what they call a continuous prompt, would be where you don't really have tokens. You add that in some deeper layer of the neural network where the text has already been converted into a vector. So your prompts are also just a vector in the same vector space. Then discrete prompts. Discrete prompts, aka hard prompts, automatically search for templates described in a discrete space, usually corresponding to natural language phrases. And then there are some methods. So for prompt mining, you have Mine Jiang et al.'s Mine approach, where it is to automatically find templates given a set of training inputs X and outputs Y. The method scrapes a large text corpora like Wikipedia for strings containing X and Y, and finds either the middle words or dependency path between the input and output. So frequent middle words or dependency paths can serve as a template X then middle words Y. So if it sees say for instance the words Tesla and Model X a lot of times with the words is a car, is made by. So it might learn Model X is made by Tesla. Then for paraphrasing, paraphrasing based approaches take in existing seed prompts, which are manually constructed or mined, and then paraphrase it into a set of candidate prompts, then selects the one that achieves the highest training accuracy on the target task. The paraphrasing can be done in a number of ways, including using round trip translation of the prompt into another language and back, using replacement of phrases from a thesaurus, or using a neural prompt rewriter specifically optimized to improve accuracy of systems using the prompt. However, Haviv et al. 2021 perform paraphrasing after the input X is input into the prompt template, showing allowing a different paraphrase to be generated for each individual input. All right. So for paraphrasing, you have all these different methods which we have discussed here. You can do back translation, which is say you translate the sentence into French, then from French back to English. So some words would be replaced by synonyms and rewritten. Then you can do replacement of phrases using a thesaurus. You can use a neural prompt rewriter, which is optimized to do this. But all of these are doing this on the prompt itself. While the approach mentioned here by Haviv et al., instead of doing this directly on the prompt, what they're doing is they're doing this on the filled prompt, not the answered prompt, but the filled prompt. So where you just have replaced this X with the correct input, and then you pass that into a paraphrasing system. Then you have gradient based search. So Wallace et al. Applied a gradient based search over actual tokens to find short sequences that can trigger the underlying pre-trained language model to generate the desired target prediction. This search is done in an iterative fashion, stepping through tokens in a prompt. So built upon this method, Shin et al. Automatically search for template tokens using downstream application training samples and demonstrate strong performance in prompting scenarios. Uh, so a gradient based search I'm not really very familiar with gradient-based searches, so let's just have a look online. What is a gradient-based search? Hmm. That doesn't really seem to be a lot. Maybe I'll just go over that paper itself. Um, I'm just going to go into the references and pull that paper out, and then let's see, maybe the abstract can help us understand what gradient based search is. Sorry for the delay. I should have read these sections earlier, but I really just like reading the paper in front of the camera first, so it also shows how I understand these works. So this paper. So they have a gradient guided search over tokens which finds short trigger sequences. All right. Um, so let's have a look at where they define this. So the trigger algorithm, we first choose the trigger length. Longer triggers are more effective while shorter triggers are more stealthy. We initialize the trigger sequence by repeating the word the subword or a character We can iteratively replace the tokens in the trigger to maximize the loss for the target prediction over batch of example. To determine how to replace the current token, we cannot directly apply adversarial attack method from computer vision. Instead, we build upon hot flip, a method that approximates the effect of replacing a token using its gradient. All right, so essentially, just from the high level idea which I got of what they're trying to do is they're trying to find samples which break the model, and to do that, they're using some seed words to initialize their trigger, and then they're trying to find the trigger sequence which maximizes the loss. So they want to get uh, okay, they want to minimize the loss for a target prediction over the batch of examples. And so why would minimizing the loss be effective? So they are replacing the token in some fashion, and then hmm, I'm not entirely sure how this works, but uh, the token replacement strategy, I guess, is pretty clear now. They are going to find words and replace them using this hot flip strategy, which would uh, using the gradient which this method approximates. And then that method then helps to pick up tokens through which you can minimize the loss for the target prediction. Maybe if I find some good resources, I'll add them down in the description. Next, we have prompt generation. Other works treat the generation of prompt as a text generation task and use standard NLG models to perform this task. For example, Gao et al. Introduces sequence to sequence pre-trained T5 into the template search process. Since T5 has been pre-trained on a task of filling in missing spans, they use T5 to generate template tokens by specifying the position to insert the template tokens within a template and provide training samples for T5 to decode template tokens. Ben David et al. 2021 proposed a domain adaptation algorithm that trains T5 to generate unique domain relevant features for each input. Then those DRFs can be concatenated with the input to form a template and can be further used for downstream tasks. So this is just generating the prompt directly from a text generation model such as T5. Then you have prompt scoring. Davison et al. Investigate the task of knowledge-based completion and design a template for an input using these head relation tail triples using language models. So this is the task of knowledge-based completion, which would be, I guess, to fill in your knowledge graph. They first handcraft a set of templates as potential candidates and fill the input and answer slots to form a filled prompt. They then use a unidirectional language model to score those filled prompts, selecting the ones with the highest LM probability. This will result in a custom template for each individual input. So this covers all our discrete prompts. And now let's have a look at the continuous prompts. So because the purpose of prompt construction is to find a method that allows an language model to effectively perform a task rather than being for human consumption, it is not necessary to limit the prompt to human interpretable natural language. Because of this, there are also methods that examine continuous prompts, which would be soft prompts, that perform prompting directly in the embedding space. Specifically, continuous prompts remove two constraints. They relax the constraint that the embedding of template words be the embedding of natural language, so like English words, and then remove the restriction that the template is parameterized by the pre-trained language model's parameters. So what do these mean? The embedding of the template words, if you had a discrete template, then it would of course be the embedding of the natural language like uh, English words, right? But since these models have seen a lot of data, when you use soft prompting, you might get an embedding which does not really correlate with English words but works really well. Secondly, you remove the restriction that the template is parameterized by the pre-trained language models parameters, because now it is not, because your template is no longer going into the language model with the input text and getting converted into the embedding. It is getting directly added after the input has already been converted into an embedding. So now let's have a look at the methods. We have prefix tuning. So prefix tuning by Lee and Liang 2021 is a method that prepends a sequence of continuous task-specific vectors to the input while keeping the language model parameters frozen. Mathematically, this consists of optimizing over the following log likelihood objective given a trainable prefix matrix M phi and a fixed pre-trained language model parameterized by phi. So you maximize the probability of yi given h less than I and the model parameters and phi, which would be the prefix matrix M of phi. So in equation 2, h less than I is a concatenation of all neural network layers at time step I. It is copied from M phi directly if the corresponding time step is within the prefix. So hi is M phi of I. Otherwise, it is computed using the pre-trained language model. Um, so I guess this just means that once you compute it, it is there in the trainable. Okay, so this just means that for some previous time steps which are within the prefix, you can directly pick them up from M of phi because it is the trainable prefix matrix. But for some others, you can also, that is computed using the language model. So experimentally, Lee and Liang 2021 observed that such continuous prefix based learning is more sensitive to different initialization in low data setting than the use of discrete prompts with real works. Similarly, Lester et al. Prepend the input sequence with special tokens to form a template and tune the embeddings of these tokens directly. Compared to Lee and Liang's 2021's method, this adds fewer parameters as it doesn't introduce additional trainable parameters within each network. Uh, Simpokeli et al. I'm really sorry for mispronouncing his name, train a vision encoder that encodes an image into a sequence of embeddings that can be used to prompt a frozen autoregressive language model to generate the appropriate caption. They show that resulting method can perform few short learning for vision language tasks, such as visual question answering. Different from the above two works, the prefix used in Simple Kelly et al. 2021 is a sample dependent, namely a representation of input images instead of task embedding. So just to go over all the works mentioned in the lecture et al. Paper, they prepend the input sequence with special tokens to form a template and tune the embedding of these tokens directly. So instead of doing the work which we saw above, this adds fewer parameters as it does not add these tunable parameters within each network layer. It just does that into the input sentence. So it is uh, tuning the embedding of these special tokens only. And in the Simple Kelly et al. Work, they have a vision encoder, and their entire task is for vision language conversion. So tuning initialized with discrete prompts. So these are methods that initialize the search for a continuous prompt uh, using a prompt that has already been created or discovered using discrete prompts. For example, Zhang et al. First define a template using a discrete search method such as auto prompt. Uh, Auto prompts. Okay, so this is uh, a possessive apostrophe s here. Auto prompts initialize virtual tokens based on the discovered prompt, then fine-tune the embedding to increase task accuracy. So they get a initial accuracy, initial embedding based on a discrete prompt, which they then optimize. This work found that initializing with manual templates can provide a better starting point for the search process. Kane and Eisner proposed to learn a mixture of soft templates for each input, where the weights and parameters for each template are jointly learned using training samples. The initial set of templates they use are either manually crafted ones or those obtained from prompt mining. So all of these methods just show that you are initializing your process using discrete prompts. And finally, in the Hambad Zumian et al. 2021's work, they introduce a user of continuous template whose shape follows a manual prompt template. So finally, you have hard soft prompt hybrid tuning. Instead of using a purely learnable prompt, these methods insert some tunable embedding into the hard prompt template. So Liu et al. Propose p-tuning, where continuous prompts are learned by inserting trainable variables into the embedded input. To account for interaction between prompt tokens, they represent prompt embeddings as the output of a BILSTM. P-tuning also introduces the use of task-related anchor tokens such as capital and relation extraction within the template for further improvement. These anchor tokens are not tuned during training. So in this work, they have some task-related tokens, anchor tokens whose template are which are present within the template. And so, for example, in relation extraction, you have the token capital, and you make sure that these anchor tokens are not tuned during the training. So your template as a whole gets tuned, but their embeddings get tuned, but the anchor tokens do not. For Han et al. 2021, they proposed prompt tuning with rules, which is PTR, where they manually crafted sub-templates to compose a complete template using logic rules. So to enhance the representation ability of the resulting template, they also insert several virtual tokens whose embeddings can be tuned together with the pre-trained language model parameters using training samples. So the template tokens in PTR contain both actual tokens and virtual tokens. Experimental results should demonstrate the effectiveness of this prompt design method in relation classification tasks. So this is sort of both hard and soft prompt hybrid tuning. Both are being used here. Then let's move on to the fifth section, which is again answer engineering. So far we were doing prompt engineering, but once the model fills in your prompt and gives you a filled prompt, how do you decode the answer out of it? So let's have a look. Answer in contrast to prompt engineering, which designs appropriate inputs for prompting methods, answer engineering aims to search for an answer space Z and to map and a map to the original input Y that results in an effective predictive model. Figure 1 of answer engineering section illustrates two dimensions that must be considered. when performing answer engineering. So you want to decide the answer shape and some answer design. For instance, some common uh, granularities are token level. So one out of the tokens in the pre-trained language model vocabulary or a subset of the vocabulary. Then you have a span, a short multi-token span. So they are usually used together with close prompts, and then you have sentence, which are usually in autoregressive tasks. So for prefix prompts. In practice, how to choose the shape of an acceptable answer depends on the task. Token or text span answer spaces are widely used in classification tasks, but are also used in tasks such as relation extraction or NER. Longer phrases or sentential answers are often used in language generation tasks, Radford et al., which I believe is a GPT paper, but also used in other tasks such as multiple choice Q&A, where the scores of multiple phrases are compared. So now design methods. So if you have the you want to design the answer space Z as well as the mapping to the output space Y if the answers are not used as the final outputs. So manual design. In manual design, the space of potential answers Z and its mapping Y are crafted manually by an interested system or benchmark designer. There are multiple ways. So you have unconstrained spaces. In many cases, the answer space Z is a space of all tokens, fixed length spans, or token sequences. In these cases, it is most common to directly map Z to the final output Y using the identity mapping. So you fill in, uh, suppose you get a bunch of tokens and you have a prefix prompt, say, then everything after the prefix prompt or everything bit in the closed prompt space is your answer. Then you have constrained spaces. However, there are some cases where the space of possible outputs is constrained. This is often performed for tasks with a limited label space, such as text classification or entity recognition, or multiple choice question answering. To give some example, Yin et al. 2019 manually designed list of words relating to relevant topics: health, finance, politics, sports, etc., emotion, or other aspects of input text to be classified. Sui et al. Manually designed lists such as person, location, etc. for NER tasks. In these cases, it is necessary to have a mapping between the answer Z and the underlying class Y. Because, say, you want to, uh, you get some emotional word, or say you get, emotion, some word denoting emotion, say, such as joy, but your class labels are positive, negative. You need to have some sort of mapping. With regard to multiple choice Q&A, it is common to use a LM to calculate the probability of an output among multiple choices. So discrete answer search. As with manually created prompts, it is possible that manually created answers are suboptimal for getting the language model to achieve ideal prediction performance. Because of this, there is some work on automatic answer search, albeit less than the search for ideal prompts. These works work both on discrete answer spaces and continuous answer spaces. So you have answer paraphrasing. These methods start with you have an initial answer space Z, then use paraphrasing to expand the answer space to broaden its coverage. So given a pair of answer and output, Z prime and Y, we define a function that generates a paraphrase set of answers. So this is just your paraphrasing function. So the probability of the final output is then defined as the marginal probability or all of the answers in this paraphrase. So this is just a summation. This paraphrasing can be performed using any method, but Jiang et al. Specifically use a back translation. So first translating into another language and back to generate multiple paraphrase answers. So anyone unfamiliar with back translation, I mentioned this earlier also. Say you have a source and a destination, and you get a paraphrased version. So this might be English to French and then back to English. So you have model 1 used here, model 2 here, or even the same model. Then you have pruned and search. So in these examples, first an initial pruned answer space of several possible answers is generated, and then an algorithm further searches over this pruned space to select a final set of answers. Note that in some of the papers introduced, they define a function from label y to a single answer token z, which is often called a verbalizer. Shake and shoots find tokens containing at least two alphabetic characters that are frequent in large unlabeled dataset. In the search step, they iteratively compute a word's suitability as a representative answer z for a label y by maximizing the likelihood of the label over training data. Shin et al. Learn a logistic classifier using the contextualized representation of the token z input. In the search step, they select the top k tokens that achieve the highest probability score using a learn logistic classifier. Those selected tokens will form the answer. Gao et al. First construct a pruned search space by selecting top k vocabulary words based on generation probability at the z position by the subsample. So just take the model probabilities over the vocabulary and then the top k. Then the search space is further pruned down by only selecting a subset of those words based on the zero shot accuracy on the training samples. In the search step, they fine tune the language model with a fixed template together with every answer mapping using training data and select the best labeled word as the answer based on the accuracy of the def set. So these are just methods which does that. So like in the first paper, in some works, they have a function which takes in label y to a single answer token z, which is called a verbalizer. So in some cases, they find tokens containing at least two alphabetic characters that are frequent in large unlabeled data. So in the search step, they iteratively compute a word suitability for uh, being the representative answer z for a label y by maximizing the likelihood of the label over training data, because you do everything over the training data. And the second one is, as we discussed, you can just use the MLM's probabilities to get the top k tokens. The label decomposition. When performing relation extraction, Shen et al. Automatically decompose each relation label into constituent words and use them as an answer. For example, uh, per city of death is then decomposed. Label words would be person, city, and death. The probability of the answer span will be calculated by as a sum of each token's probability. So again, this is just for relation extraction, specific to I guess relation extraction. Finally, you have continuous answer searches. Very few works explore the possibility of using soft answer tokens, which can be optimized through gradient descent. Hambad Zumian et al. 2021 assign a virtual token for each class label and optimize the token embedding for each class together with prompting token embeddings. Since the answer tokens are optimized directly in the embedding space, they do not make use of the embeddings learned by the language model. Instead, learn an embedding from scratch for each label. So these are some cases. I guess we haven't reached here for prompt ensembling, augmentation, and so on. Okay, so this is all a part of, I guess, this multi-prompt learning. Um, so I guess this video is around half an hour long already. I'll break this down into another part, I guess. So I'll try to cover 6 and 7 in one video and then the remaining part. So 8, 8, 9, and 10, I guess, are pretty just theoretical things, so those could be covered in one video as well. So thank you guys for tuning in. Hope to see you again next time as well. And if there's any feedback, do leave that in the comment section. Hello everyone. So I'm continuing on in this video where we were covering this paper on prompt learning, this survey paper, and sorry, prompting, and we had finished up to the fifth section, and the fifth section talked about creating your answers. So I believe it was titled answer engineering. Yeah, answer engineering. So now we'll move on to the sixth section, which is multi-prompt learning. All right. So the prompt engineering methods we discussed so far focus mainly on constructing a single prompt for an input. However, a significant body of research has demonstrated that the use of multiple prompts can further improve the efficacy of prompting methods. And we will call these methods multi-prompt learning methods. So in practice, there are several ways to extend the single prompt learning to multi-prompt, and they'll summarize all of them. So first of all, you have prompt ensembling. So prompt ensembling is a process of using multiple unanswered prompts for an input at inference time to make predictions. So an example is figure 4a. So you have these prompts. China's capital is dash is the capital of China, and the capital of China is dash, and then you combine all of them and give that as input. So this sort of prompt ensembling can leverage the complementary advantages of different prompts, alleviate the cost of prompt engineering since choosing one best performing prompt is challenging, it varies from case to case, and stabilize performance on downstream tasks. Because some prompts might work better than the other in some cases and so on, but on an average, they'll hopefully be stable. Prompt ensembling is connected to ensembling methods that are used to combine together multiple systems which have a long history in machine learning, so of course, random forests and so on. Current research also borrows ideas from these works to derive effective ways from prompt ensembling as described below. So you have uniform averaging. The most intuitive way to combine the predictions when using multiple prompts is to take average of probabilities from different prompts. So concretely, this indicates that you're just averaging over the probability of the tokens, where this is the prompt for the ith prompt. This is the function for the ith prompt. Jiang et al. First filter these prompts by selecting k prompts that achieve the highest accuracy in the training set, and then use the average log probabilities obtained from the top k prompts to calculate the probability of for a single token at z. So this is like uh, each prompt would give a probability distribution at z for tokens, and then they can just uniformly average that. So this was when performing factual probing tasks. There you can have a single answer. Schick and Schurz also try a simple average when using ensemble method to annotate an unlabeled dataset. When performing text generation, Yuan et al. Formulate the task as a text generation problem and take average of the final generation scores obtained using different prompts. So you can just see how this is happening. So suppose this gives a distribution of uh, Beijing with probability point 2, Shanghai with probability point 1, and so on. Then here also you'll get a similar distribution. Let's say this prompt failed and it said Delhi with a probability of point 0.3, which is the capital of India and not China. And then Beijing is the second one with say probability point 0.1. But the third one again gave a similar distribution as the first one, but having different probabilities. On an average, when you average up these probability distributions over the tokens, Beijing would hopefully be the best answer or the answer with the highest probability mass. Then you have weighted averaging. So instead of simple averaging, you can also in the case of simple averaging, you are giving equal weightage to every prompt, but some prompts might be better than others. So to account for this, you can have a weighted average for prompt ensembling, where each prompt is associated with a weight. The weights are typically pre-specified based on prompt performance or optimized using a training set. For example, Jiang et al. Learn the weight for each prompt by maximizing the probability of a target output over training data. Kin and Eisner 2021 use the same approach except that the weight for each prompt is optimized together with soft prompt parameters. Besides, Skin and Eisner 2021 also introduced a data-dependent weighting strategy where the probability of the input appearing in that prompt is also considered in the weighting of different prompts. So, uh, the probability, I guess this is just learned from the training set. So, if the prompt occurs in the training data, then is the input likely to occur in that and so in the placeholder place and so on. She can shows 2021 A and B set the weight for each prompt proportional to the accuracy in the training set before training. So this seems like a more intuitive way. So the first and the third way. The second one also looks pretty ingenious, if I must say. But all of these like make a lot of sense. Then you have majority voting. For classification tasks, majority voting can also be used. So the highest probability mass. So I guess you are just using Instead of averaging over the probabilities, you're just taking the one which has the highest absolute probability across all distributions. That could be one way. Then you have knowledge distillation. An ensemble of deep learning models can typically improve the performance, and this superior performance can be distilled into a single model using knowledge distillation. So to incorporate this idea, Schick and Schultz train a separate model for each manually created template answer pair and use the ensemble of them to annotate an unlabeled dataset. Then the final model is trained to distill the knowledge from the annotated dataset. Gao et al. 2021 uses similar ensemble method on their automatically generated templates. So what they're trying to do is they're trying to extract knowledge from an ensemble of deep learning models, so multiple deep learning models. To do this, they create some pairs and they get it annotated by the ensemble, and the final model learns on that annotated dataset, so it gets knowledge from all the models, hopefully. Again, there are no guarantees, but there are no guarantees anywhere in deep learning. Then you have prompt ensembling for text generation. So there's relatively little work on prompt ensembling for generation tasks, tasks where the answer is a string or token of string. A simple way to perform ensembling in this case is to use standard methods that generate the output. Sorry about that. Based on the ensemble probability of the next word in the training sequence. In contrast, Schake and Schultz train a separate model for each prompt, and and thus storing each of these fine-tuned language models in memory is infeasible. Instead, they first decode generations using each model and then score each generation by averaging the generation probability across all models. So I guess they are just uh, okay. Let me just read that again. A simple way to perform ensembling in this case is to use standard methods that generate the output based on ensemble probability of the next word in the answer sequence. So the next token is you give the input prefix prompt or anything which you've decoded so far, and then all the models predict the next token, and the token with the highest probability is chosen, and then that is again fed by appending that to the input string to the next time step of decoding. Then you have prompt augmentation. Prompt augmentation, also called demonstration learning, provides a few additional answered prompts that can be used to demonstrate how the language model should provide the answer to the actual prompt instantiated with the input text. For example, instead of just providing a prompt of China's capital is Z, the prompt can be prefaced by example, Great Britain's capital is London, Japan's capital is Tokyo, China's capital is Z. So this would give the model more context about what they're looking for. Another example of performing addition of two numbers can be found in figure 4b. These few demonstrations take advantage of the ability of strong language models to learn repetitive patterns. Although the idea of prompt augmentation is simple, there are several aspects that make it challenging. So, how do you select samples which are effective, and how do you order them? So, before that, let's just have a look at the example which they mentioned. So you show it two prompts. 1 plus 1 is 2, 2 plus 5 is 9, and then 6 plus 8 is mask, and then the model has to guess. But now the model at least knows, hopefully knows your intention. For sample selection, researchers have found that the choice of samples used in the few shot scenario can result in very different performance, ranging from near state of the art to near random guesses. To address this issue, Gao et al. And Liu et al. Utilize sentence embeddings to sample examples that are close to the input in embedding space. To measure the generalization capability of pre-trained language models to perform new tasks based on instruction, Mishra et al. Provide positive samples and negative samples that highlight things to avoid. So these are just some heuristics. Uh, so the first heuristic is taking examples whose embedding are closer in the embedding space, and the second method is giving both positive and negative samples. So the positive samples tell it what to do, and the negative samples tell it what not to do. For sample ordering, again, Liu et al. 2021 found order of answered prompts provided to the model play an important role in model performance and provide entropy-based methods to score different candidate permutations. Okay, Kumar Talukdar 2021 search for a good permutation of training examples as augmented prompts can learn a separate token a separated token between prompts for further gain in performance. So uh, they just look for good permutation of training example as augmented prompts, and they have a special separator token which is also learned, which tells the model, okay, these are distinct prompts or distinct examples. Prompt augmentation is closely related to retrieval based methods that provide more textual context to the model to improve performance, a method that has been shown to be effective in prompt based learning. However, the key difference lies in the fact that prompt augmentation also leverages the template and answer, while the larger context learning does not. Again, so we are now on to the third one, which is prompt composition. For composable tasks, which can be composed based on more fundamental subtasks, we can perform prompt composition using multiple subprompts, each for one subtask, and then defining a composite prompt based on those subprompts. So you take multiple subprompts for different subtasks and create a composite prompt for all of those tasks. This is only valid for composable tasks. For example, in the relation extraction task, which aims to extract the relation of two entities, we can break down the task into several subtasks, including identifying the characteristic of entities, classifying the relationship between entities, and so on. So based on this intuition, Han et al. First used multiple naturally created subprompts for entity recognition and relation classification, and then composed them into a complete prompt based on logic rules for relation extraction. So I guess this is pretty self-explanatory why prompt composition works. So let us now have a look at some example on prompt composition. For instance, Google became a subsidiary of Alphabet as the input. Then you have X the mask Google, X the mask Alphabet, X Google mask Alphabet. So these are sub prompts, and then you can combine them. So what this basically does is now the model uh, is doing multiple tasks which were composable before together. And this also gives the model more idea about, okay, maybe just having one token to fill does not give it enough context, but seeing, okay, I also need to fill those things, or the model probably doesn't know that it needs to fill those things, but it knows there is some context ahead as well, which can be used. Then you have prompt decomposition. So what tasks where multiple predictions should be performed for one sample, like sequence labeling. Directly defining a holistic prompt with regard to the entire input is challenging. One intuitive method to address this problem is to break down the holistic prompt into different subprompts and then answer each subprompt separately. So figure D shows this for NER, which aims to identify all entities and inputs. In this case, the input will first be converted into a set of text spans, and the model can then be prompted to predict the entity type. So, like including not an entity for each span. It is not easy to predict all the span types at the same time due to large number of spans. So different prompts for each span can be created and predicted separately. This sort of prompt decomposition for named entity recognition has been explored by Suri et al. So again, going back to the example, you had this sentence, Mike went to New York yesterday, and then you create two prompts, X Mike is mask entity type, and then New York is mask entity type. These are two prompts, and then you can create sub prompts from that. So I think this entire section on prompt augmentation is not prompt augmentation, multi-prompt learning is clear now. So this is a part of the broader, uh, like this is a section of the paper which is now completed. So now we'll be moving on training strategies for prompting methods. So far we've just seen how do we build prompts, right? How do we train the models when we have prompts? With the methods in the above section, it is now clear how to obtain an appropriate prompt and the corresponding answers as well. Now let's discuss about methods that explicitly train model in concert with prompting. So training settings. In many cases, prompting methods can be used without any explicit training of the language model for the downstream task. Simply take a language model trained to predict probability effects and applying it as is to fill the close or prefix prompts defined to specify the task. So this is what you call zero shot, where you do not tell it anything. However, there are also methods that use training data to train the model in concert with prompting methods. These either consist of again full data learning, where a reasonable large number of training examples are used to train the model, or few short learning, where a very small number of examples are used to train the model. Prompting methods are particularly useful in the latter case as there are generally not enough training examples to fully specify the desired behavior, and thus using a prompt to push the model in the right direction is particularly effective. One thing to note is that many of these prompt engineering methods described in section 4, although annotated training samples are not explicitly used in the training of the downstream task model, they are often used in the construction or validation of the prompts that the downstream task will use, because you can't just create prompts, right? You also need to test how good they are. Something might seem very reasonable to a human, but it might just break down in front of a machine. This is arguably not true zero shot learning with respect to the downstream tasks, as you're again doing some sort of validation beforehand for your prompts. But who cares till it works, right? Although claiming it is zero shot might be wrong. Then you have parameter update methods. So far we were just seeing the training settings. So in prompt-based downstream task learning, there are usually two types of parameters, namely those for the pre-trained models and the prompts. Which part of parameter should be updated is one important design decision, which can lead to different levels of applicability. We summarize 5 tuning strategies based on whether the parameters of the underlying language model are tuned, whether there are additional prompt related parameters, if there are additional prompt related parameters, whether those parameters are tuned. So this basically just differentiates your training methods into what all parts of the model are being trained. So is it just training the model, or is it also training the prompts? So for instance, you have promptless fine tuning where the parameters are tuned. Then you have tuning free prompting, then fixed language model prompt tuning. So I guess they'll be discussed in detail below, right? So let's have a look at first promptless fine tuning. As mentioned in introduction, the pre-train and fine-tune strategy has been widely used in NLP since before the popularization of prompting methods. So pre-training and fine-tuning without prompts are called promptless fine-tuning, to contrast with the prompt-based learning methods introduced in the following section. In this strategy, given a data set, all or some of it, of the parameters of the pre-trained language model will be updated via gradients induced from the downstream training sample. So, like sentiment classification. Typical examples are BERT and Robota. This is simple, powerful, and widely used method, but it may overfit or not learn stably on small data sets. Models are also prone to catastrophic forgetting, where the language model loses its ability to do things that it was able to do before fine-tuning. So advantages again, simplicity. There is no need for prompt design because uh, you're not you're doing promptless, right? You have no prompts, and tuning all parameters, language model parameters allows the model to fit to larger data. So and the disadvantages are overfitting and no not stable training on smaller data sets. Then you have tuning free prompting. Tuning free prompting directly generates the answers without changing the parameters of the pre-trained language models based only on a prompt. These can be optionally augmenting inputs with answered prompts as described in section 6.2, and this combination of tuning free prompting and prompt augmentation is also referred to as in-context learning. All right. Typical examples of tuning free prompting include Llama and GPT-3. So in here you are just generating the answer without changing any of the language model parameters and only using the prompt. So similar to how people played around with GPT-3. So advantages, since there are no parameter updates, there is efficiency, there is no catastrophic forgetting since the models are parameters are frozen, and it is applicable in zero shot settings. Disadvantages is because uh, prompts, the only task specific information are going in through the prompts, then you need to have very good prompts to achieve high accuracy. And in particular, in the in context learning setting, providing many answered prompts can be slow at test time and thus cannot be easily used uh, on large training data sets, because uh, if you have multiple many answered prompts, then you need to get them from somewhere, right? You need to process them. Fixed language model prompt tuning. So in this case, additional prompt relevant parameters are introduced based on besides the parameters of the pre-trained model. So fixed language model prompt tuning updates only the prompts parameter using the supervision signal update from the downstream training samples while keeping the entire pre-trained language model unchanged. So here your language model remains unchanged, only your prompts are being tuned. So the examples of prefix tuning and warp. So advantages are similar to tuning free prompting. It can retain knowledge in language models since their parameters are not updated and is suitable in free few short scenarios. And of course, tuning it gives better accuracy than tuning free prompting in many cases. It is not applicable in zero shot scenarios. While effective in few short scenarios, representation power is limited in large data settings because you cannot use all of it. And then prompt engineering, though through choice of hyperparameters or seed prompts is necessary. And prompts are usually not human interpretable or manipulable because your prompts are like parameters that are updated. So you maybe you know what the initial prompt was, but after some updates you don't know. Then you have fixed prompt language model tuning. Fixed prompt language model tuning tunes the parameters of a language model, as in the standard pre-train and fine-tune paradigm, but additionally uses prompts with fixed parameters to specify the model behavior. So this potentially leads to improvements, particularly in few short scenarios. So here, it's like you have your pre-train and fine-tune paradigm. You are tuning the language model parameters, but you are keeping your prompts fixed. So the prompt parameters are not tuned. So the most natural way to do is to provide a discrete textual template that is applied to every training and test example. So you just add it your uh, your input into that template. Some example are PET-TC, PET-CHIN, and LMBFF. Logan 4 et al. 2021 more recently observed that prompt engineering can be reduced by allowing for a combination of answer engineering and partial language model fine-tuning. For example, they define a very simple template, null prompt, where the input and mask are directly concatenated without any template words, and find this achieves competitive accuracy. So your model is just learning to parse these prompts. So advantages: prompt or answer engineering more completely specify the task, allowing for more efficient learning, particularly in the case of few short scenarios. And disadvantage: prompt or answer engineering are still required, which is again expensive and difficult, although perhaps not as much as without prompting. Language models fine-tuned on one downstream task may not be effective on another one. So again, these are some of the disadvantages. Then finally, you have something which does everything, prompt plus language model tuning. In this setting, there are prompt element parameters which can be fine-tuned uh, together with all or some of the parameters of the pre-trained model. Representative examples include PADA p-tuning and p-tuning. Notably, this setting is very similar to standard pre-train and fine-tune, just having some additional prompt parameters. Advantages: this is the most expressive method because you have all of the world's parameters at your disposal to train. Disadvantages: it requires training and storing all parameters of the model, and it may overfit to smaller data sets. So I think this is pretty clear now. What are these five different tuning strategies? Again, if you go back to the table, promptless fine tuning, your language model parameters are already tuned. You are not doing anything. You're just asking the MLM to fill in words. Then you have tuning free prompting where nothing is tuned. Then you have fixed language model prompt tuning where your additional language model is fixed but your prompts are being tuned. Then you have fixed prompt language model tuning where your prompts are fixed but your language models are tuned. And then you have prompt plus language model fine tuning where both of them are tuned. So with this we finish section 7 and move on to section 8. So in previous sections, we examined prompting method from the point of view of the mechanism of the method itself. In this section, we rather organize prompting methods from the point of view of which application they have been applied to. So where are they being used? So knowledge probing, factual probing. So factual probing or fact retrieval is one of the earliest scenarios with respect to which prompting methods were applied. The motivation of exploring this task is to quantify how much factual knowledge the pre-trained language model's internal representations behavior. So in this task, the parameters of the pre-trained model are usually fixed and knowledge is retrieved by transforming the original input into a closed prompt, which can be manually crafted or automatically discovered. Relevant datasets including llama and X factor, including I guess it should be include, not including. Since the answers are predefined, fact retrieval only focuses on finding effective templates and analyzing the results of different models using these templates because your answers are fixed one words or few words, I guess. Both discrete template search and continuous template learning have been explored, as well as prompt ensembling. All right. For linguistic probing, besides factual knowledge, large-scale pre-trained learning also allows language model to learn handle linguistic phenomena such as analogies, negations, semantic role sensitivity, semantic similarity, cant understanding. I'm not really sure what that is, and rare word understanding. The above knowledge can be elicited by presenting linguistic probing tasks in the form of natural language sentences that are completed by the language model, so you understand where does it fail or does it truly understand the linguistic phenomena. Then you have your classification based tasks. So prompt based learning has been widely explored in classification based tasks where the prompt templates can be constructed relatively easily, such as text classification and natural language inference (NLI). The key to prompting for classification tasks is reformulating it as an appropriate prompt. So you can use a prompt like the topic of this document is Z, which is then fed into a masked pre-trained language model for your slot filling. For text classification, most previous work has used closed prompts, and both prompt engineering and answer engineering have been explored extensively. Most existing works explore the efficacy of prompt learning for text classification in the context of few shot and fixed prompt language model tuning. Then you have natural language inference. It aims to predict the relationship, like entailment of two given sentences. Similar to text classification, for NLI tasks, closed prompts are commonly used. Regarding prompt engineering, researchers mainly focus on the template search in the few shot learning setting, and the answer space is manually pre-selected from the vocabulary. This is just a table of different model methods. So these are work different prompting works, and let's just look at the column names, the tasks they use on the pre-trained language model uses setting, prompt engineering done or not, answer engineering done or not, tuning done or not. What's mul PR? I'm not entirely sure. What's the last column? Okay, so they have mul-PR column lists multiple prompt learning methods. So which of those? Okay, these are just abbreviations for that. For information extraction, unlike classification tasks where closed queries can be intuitively constructed, uh, these for these tasks it is much more difficult, as you might guess. For relation extraction, uh, here you need to predict the relationship between entities in a sentence. Shen et al. First explored the application of fixed prompt language model tuning and discussed two major challenges that hinder the direct inheritance of prompting methodology. You have a larger label space like 80 relations versus 2 in sentiment classification, which results in more difficulty in answer engineering. And in relation extraction, different tokens in the input sentence may or may not be less important. So, like entity mentions are more likely to participate in a relation than, say, some adjective, which, however, can not be easily reflected in the prompt template for classification since the original prompt template regards each word equally. To address these problems, Shen et al. Propose an adaptive answer selection method to address the issue. Task-oriented prompt templates constructed for the issue, where they use special markers like E to highlight the entity mentioned in the template. So this gives the model more information about where the entities are. Han et al. 2021 incorporate entity type information via multiple prompt composition techniques. Then you have semantic parsing. Semantic parsing is a task of generating structured meaning representation given a natural language input. Shen et al. 2021 explored the task of few short semantic parsing using language models by framing the semantic parsing task as a paraphrasing task, constraining the decoding process by only allowing the output valid according to the grammar. So this allows you to do semantic parsing by having these additional layers involved. They experiment with the in-context learning setting, choosing answered prompts that are semantically close to the given test example. determined by the conditional generation probabilities of generating a test sample given another training sample. The result demonstrates the effectiveness of paraphrasing reformulation for semantic parsing tasks using pre-trained language model. So again, what is semantic parsing? It is generating the structured meaning representation given an input, and for this, uh, you need the best results were obtained by framing the semantic parsing task as a paraphrasing task where you ask the model to paraphrase it, and then you constrain the decoding process by only allowing valid output valid according to a grammar which you have. Then for NER, the task is identifying named entities. The difficulty of prompt-based learning application to tagging task is exemplified as NER because each unit to be purchased a token of span. There is a latent relationship between the token label, and overall the application of prompt-based learning in tagging tasks has not been fully explored. So Sui et al. Recently proposed a templates-based NER model using BART, which enumerates text spans and considers the generation probability of each type within manually crafted templates. So, for example, you have this Mike went to New York yesterday. To determine what type of entity Mike is, they use a template Mike is a Z entity, and the answer space Z consists of values such as person and organization. Then you have reasoning in NLP. There's a debate about if deep neural networks are capable of performing reasoning or just mentioning, or they are just memorizing patterns. So there have been a number of attempts to probe language models' reasoning ability by defining benchmark tasks that span different scenarios, and some of them are discussed here. So after this, I guess we have a couple of more applications and some resources, and I'll probably end there. And these last few sections, uh, I'll cover them in a final video on this topic. Alright, so for common sense reasoning, there are a number of benchmark datasets testing common sense reasoning. Some commonly ones have Vinograd schemas, which require the model to identify the antecedents of an ambiguous prompt within the context or involve completing a sentence given multiple choices. For the former, an example could be the trophy doesn't fit into the brown suitcase because it's too large, and the task for the model is to infer whether it refers to the trophy or the suitcase. So this is just common sense which us humans can easily uh, re- figure out, right? So by replacing the word it with its potential candidates in the original sentence and calculating the probability of the different choices, pre-trained language models can perform quite well by choosing the choice that achieves the highest probability. For the latter, an example could be Eleanor offered to fix her visitor some coffee. Then she realized she didn't have a clean Z. And again, the candidate choices are cup, bowl, or spoon. The task for the pre-trained language model is to choose the one from the three candidates that most conforms to common sense. For these kinds of tasks, you can score the generation probability of each candidate and choose the one with the highest probability. So just look into your vocabulary post softmax, and then in the words which you're particularly interested in, see which one has the highest probability. So mathematical reasoning is the ability to solve mathematical problems like arithmetic addition, function evaluation. Within the context of pre-trained language model, researchers have found that pre-trained embeddings in language models can perform simple operations such as addition and subtraction when the number of digits is small, but fail when the digits are larger. Some works explore more complex mathematical functions like exponential and nested functions, a reasoning problem, and improve the language model performance to serializing functions for the operation. So you first tell it what is f of x, then you tell it you want f of 3. So as a human, I can see that would be 81, hopefully. So 3 into 3, 9, and then 9 into 9, 81. For Q&A, you have the task is to extract a given answer the question, often based on a context. Q&A can take a variety of forms. So you have extractive Q&A where you extract the answer, which is squad, multiple choice Q&A, like race and free form Q&A, where the model returns an arbitrary textual string as a response, like narrative Q&A. Generally, these different formats have been handled using different modeling frameworks. One benefit of solving Q&A problems with LMs, potentially using prompting methods, is that different formats of QA tasks can be solved within the same framework. So you don't need specific modeling frameworks. For example, Khashabi et al. Reformulate many QA tasks as just text generation problems by fine-tuning sequence-to-sequence based pre-trained models like T5 and appropriate prompts from the context and question. Jiang et al. Take a closer look at such prompt-based QA system using sequence-to-sequence pre-trained model like T5 bar GPT-2 and observe that the probabilities from these pre-trained models on QA tasks are not very predictive of whether the model is correct or not. I don't think GPT-2 is a sequence-to-sequence model. I think it's just, a, I guess it can be treated like one, but I'm not sure if it is truly one because it does not have an encoder like T5 and BART do. For text generation, you have it is a family of tasks that involve generating text, usually conditions some other piece of information. Prompting methods can be easily applied to these tasks by using prefix prompts together with autoregressive pre-trained language models. Radford et al. 2019 demonstrated impressive ability of such models to perform generation tasks such as text summarization and machine translation using prompts such as translate to French. Brown et al. Performed in-context learning for text generation, creating a prompt with manual template and augmenting the input with multiple answered prompts. Schick and Schultz 2020 explored fixed prompt LM tuning for few short text summarization with manually crafted templates. Li and Liang 2021 investigate fixed language model prompt tuning for text summarization, data to text generation, few short setting where learnable prefix tokens are prepended to the input while parameters and pre-trained models are kept frozen. Dow et al. Explored the prompt plus language model tuning on text summarization, where learnable prefix prompts are used and initialized by different types of guidance signals, which can then be updated together with the parameters of the pre-trained language models. So if I seem like I'm going too fast, I am because this is not something which I can really explain. These are just works which have happened, and this is things which they have done. So I believe if we reach this part, you truly understand what all of this means. For automatic evaluation of text generation, Yuan et al. Have demonstrated that prompt learning can be used for automated evaluation. Specifically, they conceptualize the evaluation of generated text as a text generation problem model using a pre-trained sequence-to-sequence model, and then use prefix prompts that bring the evaluation task closer to pre-trained tasks. They experimentally find that simply adding the phrase such as the translated text when using pre-trained models can significantly cause improvement in German to English MT. For multimodal learning, Simpo Kelly et al. Shift the application of prompt learning from text-based NLP to multimodal setting. They specifically represent each image as a sequence of continuous embeddings, and a pre-trained language model whose parameters are frozen is prompted with a prefix to generate text to its image caption. Empirical results show few short learning ability with the help of a few demonstrations. Systems can rapidly learn words for new objects and novel visual categories. So this is now extending your models to more embedding spaces. For meta applications, you have domain adaptation. So practice of adapting a model from one domain like news to social media. And for this, you use self-generated DRS, which are domain-related features, to augment the original input. For debiasing, this is just self-diagnosing the issues in the model and debiasing based on some instructions. So you have, say, the input, the following text contains valence xz, then we fill x with input and then look at the generation probability at z. If the probability is yes or no, then we can know what it is. Then to perform debiasing, we first compute the probability of next word, then we compute the probability of next word by appending self-diagnosis textual input. As mentioned, the two probability distributions can be combined to suppress the undesired attribute. For dataset construction, you can just use it to write two sentences that mean the same thing, and then you attempt to generate sentences that creates datasets in an automated fashion. And here are some resources for the same. So I'll be ending this video here. This is already around 40 minutes long, and I guess we'll have around one more video. Yeah, that I think should do it because a lot of the remaining paper is just tables and stuff, and that would finish us up for this paper. So thank you guys for tuning in. Hope to see you next time as well. Hello everyone. So in today's video, we are going to go over the remaining parts of this prompting survey paper. So we have reached topic 9, which is prompt relevant topics, and let's just try to finish this paper up in this video. All right. So in this section, we connect prompt learning with other similar learning methods. So first we have ensemble learning. It is a technique that aims to improve the performance by taking advantage of the complementarity of multiple systems. So generally the different systems result from different architectures, training strategies, data ordering, or different initializations. So in prompt ensembling, the choice of prompt templates becomes another way to generate multiple results to be combined. And this has a clear advantage that this does not necessarily require training the model multiple times. For example, when using discrete prompts, these prompts can simply be changed during the inference, and you don't really need to train it with different prompts. Then you have few shot learning. Few shot learning aims to learn a machine learning system in the data scarce scenarios with fewer training examples. There are a wide variety of methods to achieve few shot learning, including model agnostic meta learning. Then you have where you learn features rapidly, adaptable to new tasks. Then you have embedding learning, embedding each sample in a low dimensional space where similar samples are close together. Memory based learning, so representing each sample by a weighted average of content from the memory, and so on. So prompting augmentation can be regarded as another way to achieve few shot learning. So where you are priming based few shot learning. So compared to previous methods, prompt augmentation directly preprints several labeled samples to the currently processed sample, elicit knowledge from pre-trained language model even without any parameter tuning. So you just show it a few samples and then the model learns okay, the model learns, okay, this must be expected out of me. So you have this table. Uh, so these are just some research topics. I guess you can go over them yourself. These are pretty self-explanatory. Then larger context learning. Larger context learning aims to improve the system's performance by augmenting the input with additional contextual information. So this can be retrieved from the training set or some external data sources. So for instance, in the case of say Twitter, say some Twitter sentiment analysis, the user's previous tweets or the user's bio might be a relevant feature which you can extract from external data sources. Prompt prompt augmentation can be regarded as adding relevant labeled samples into the input, but a minor difference is in larger context learning. The introduced context is not necessarily labeled data. It can be anything, right? So, for instance, the user's bio is not related to the tweet directly, but it's just information. Then you have query reformulation. Query reformulation is typically used in information retrieval tasks and Q&A tasks, which aim to elicit more relevant text or document or answers by expanding the input query with related query terms or generating paraphrase. So the same prompt would here in terms of prompt, you'll just have the same prompt in different ways. So there are several commonalities between prompt-based learning and query reformulation. So both aim to make better use of existing knowledge bases by asking the right questions. The knowledge bases are usually black boxes not available to the users, so researchers must learn how to probe it optimally based on solely the question which the user asks. So there are also differences. The knowledge base is traditionally query in traditional query formulation problems usually a search engine, or a QA system. By contrast, for prompt-based learning, this knowledge base is an LM, and we need to find the appropriate query to elicit an appropriate answer from it. So the input formulation, reformulation in prompt learning has changed the form of task. For example, an original text classification task has been converted into a close question problem, therefore bringing additional complexity. So you need to formulate it well, you need to change the modeling framework accordingly. So maybe just looking at the CLS tokens embedding is no longer the solution, right? You need to opt for a MLM and so on. These steps are not required in traditional query formulation. Despite these discrepancies, some methodologies from query reformulation research still can be borrowed for prompt learning, such as decomposing input query into multiple subqueries, which is similar to how to decompose prompts, which we saw before. So QA-based task formulation. QA-based task formulation aims to conceptualize different NLP tasks as a question answering problem. So Kumar et al., McCain et al. Our earlier works that attempt to unify multiple NLP tasks into a QA framework. Later, this idea has been further explored in information extraction and text classification. These methods are very similar to the prompting introduced here in that they use textual questions to specify which task is to be performed. However, one of the key points of prompting methods is how to better use the knowledge in pre-trained language models, and these were not covered extensively on previous works advocating for QA formulation. So you ask the model uh, the query in form of a question and don't really care about optimally probing the model's factual storage. Then control generation, it aims to incorporate various types of guidance beyond text into text generation models. So specifically, guidance signal could be style tokens. So for style transfer, length specifications, domain tags, or any variety of piece of information used to control the generated text. It can also be keywords, relation triplets, or even highlighted phrases or sentences to plan the content of the generated text. In a way, many of the prompting methods described here are a type of control generation where the prompt is usually used to specify the task itself. Thus, it is relatively easy to find commonalities between the two genres. So both add extra information to the input text for better generation, and these additional signals are often learnable parameters. And if control generation is equipped with sequence to sequence based pre-trained model like BART, then it can be regarded as prompt learning with input dependent prompt and the prompt plus language model fine tuning strategy because you're training both BART and the prompts. So one example is GSUM, where both the prompts and the pre-trained language parameters can be tuned. Also, some clear discrepancies are there. So, in control generation work, the control is generally performed over the style or content of the generation, while the underlying task remains the same. They don't necessarily require a pre-trained model. In contrast, the main motivation for using prompts is to use the pre-trained models, right? So you only want to specify the task and better utilize the pre-trained model. Moreover, most of the current work on prompt learning and text generation shares a dataset or task level prompt. Only very few works have explored input-dependent ones. However, there is common setting and effective. Uh, they, this is a common setting and effective in the control text generation, which may provide valuable direction for future work. So, what does these last 2 points mean? What do these last 2 points mean? So, for the second point, the current works in prompt learning share a data set or a task level prompt. So, these are the prompts are specific to say sentiment analysis and so on. Only very few features have works have explored input dependent ones. So you don't really change your prompt based on the input itself. So if you're doing sentiment analysis, all of them will follow the same template in most cases and won't change based on what the input is. So for supervised attention, knowing to pay attention to the important information is a key step when extracting useful information from objects such as long text sequences, images, or knowledge bases. So supervised attention aims to provide explicit supervision over the attention of models based on the fact uh, complete, completely data-driven attention can overfit to some artifacts. So in this aspect, prompt learning and supervised attention share ideas that both aim to extract salient information with some clues which need to be provided separately. So to solve this problem, supervised attention methods try to use additional loss function to predict goal attention on a manually labeled corpus. Research and prompt learning may also borrow ideas from this literature. So this is some, if you're familiar with the hate explain paper, they also do something like this only. So I'll just show you a diagram to explain. I believe that would be the fastest way. So when you just leave attention to learn the model to learn the attention weights on its own, it might learn some spurious correlations. You might want to force the model to learn in some particular way. So you can annotate your data to know which words the model should pay more attention to, and then use that. Uh, Let me just go to the right figure. Yeah, use that predicted attention over the words and the attention which is the grounded attention which you manually annotate and compare them and try to bring the predicted attention close to the grounded attention. So this will force the model to not learn spurious attention relations, right? For data augmentation, it is a technique that targets increasing the amount of data that can be used. by making modifications to existing data. As recently observed, adding prompts can achieve similar accuracy improvement to the addition of hundreds of data points on average across classification tasks, which suggests that using prompts in a downstream task is similar to conducting data augmentation implicitly. So maybe different prompts query different chambers of the model's brain finally. So we finished section 9. Now we're moving on to section 10. Section 10 is on the challenges. So for prompt design, tasks beyond classification generation, most existing works about prompt-based learning revolve around either classification or generation because they are the most important ones and the most used ones as well. Applications to information extraction and text analysis tasks have been discussed less, largely because the design of prompts is less straightforward. We expect that applying prompting method to these tasks in the future will require either reformulating or that they can be solved using classification or text generation based methods, or performing effective answer engineering that expresses structured outputs in an appropriate textual format. So just adapting to newer different methods. Prompting with structured information. So in many NLP tasks, the inputs are imbued with some variety of structure, like a tree, graph, table, or relational structure. How to express best these structures in prompt or answer engineering is a major challenge because you want to give optimally probe the model's information, right? So existing works make a step by making prompts with additional marks to encode lexical information such as entity marking. Agha et al. 2021 presents structured prompts based on hypertext markup language for more fine-grained web text generation. So I guess they are giving it H1 tags and so on, so it knows what it needs to generate, right? Because the model has seen a lot of HTML documents as well. However, moving beyond this to more complicated varieties of structures is largely unexplored. So maybe this could be like a SQL query or a knowledge graph query. Entanglement of template and answer. The performance of a model will depend on both the templates being used and the answer being considered. How to simultaneously search or learn for the best combination of template and answer remains a challenging question. So current works typically select answers before they select template. Uh, typically select answer before select template, but the work by Hambad Zumian et al. 2021 have demonstrated the initial potential of simultaneously learning both. So learning the answer and the templates together. Then you have answer engineering. So these were all for prompt designing. Now for answer engineering, you have many class and long answer classification tasks. So for classification based tasks, there are two main challenges. When there are too many classes, how to select an appropriate answer space becomes difficult. Uh, and when using multi-token answers, how to best decode multiple tokens remains unknown. Although some multi-token decoding strategies have been proposed. So if you want to say decode two tokens in a blank, how would you do that in the most optimal way? Multiple answers for generation tasks. So for text generation tasks, qualified answers can be semantically equivalent but syntactically diverse. Because you can have multiple ways to answer the same thing. So far, almost all works use prompt learning for text generation, relying solely on a single answer with only a few exceptions. How to better guide the generation process with multiple references remains a largely open research problem. And then the selection of tuning strategy, as selected discussed, you have a variety of tuning parameters of prompts, language models, or both. However, given the nascent stage of this research field, we still lack a systematic understanding of the trade-offs between these methods. The field could benefit from systematic exploration, such as those performed in the pre-trained and fine-tuned paradigm regarding the trade-off between these different strategies. So these are all the problems with or the challenges with learning your answers. So answer engineering. Then for multi-prompt learning, you have prompt ensembling. So in prompt ensembling method, the space and time complexity is pretty high. How to distill the knowledge from different prompts remains unexplored. So some works use an ensemble model to annotate a large dataset to distill the knowledge from multiple prompts. In addition, how to select ensemble worthy prompts is also underexplored. So for text generation, the study of prompt ensemble learning has not been performed so far because some ensemble learning in text generation itself is relatively complicated. To remedy this problem, some recent proposed neural embedding and ensembling models such as refactor could be considered as a method for prompt ensembling in text generation. So essentially, the issues with prompt ensembling. Then you have prompt composition and decomposition. Both of them aim to break down the difficulty by introducing multiple sub prompts. So in practice, how to make a good choice between them is a crucial step, because if you create worthless sub prompts, then your downstream performance decreases. So empirically, for token or span prediction tasks, prompt decomposition can be considered, while for span relation prediction tasks, prompt compositions would be a better choice. In the future, the general idea of decomposing or composing can be explored in other scenarios apart from just NER or entity co-reference resolution. Now, prompt augmentation. Existing prompt augmentation methods are limited by the input length. So, feeding 2 minute demonstrations to the input is feasible, because then your attention is very uh, split up, right? So, it doesn't really pay, it might not pay the right amount of attention to every word where you really want the attention to be. And it might again start suffering from like long range problems. Therefore, how to select informative demonstrations and order them in an appropriate is an interesting but challenging research problem. For prompt sharing, all the above considerations refer to the application of prompt in a single task, domain, or language. We may also consider prompt sharing, where prompt learning is applied to multiple tasks, domains, or language. Some key issues may arise, including how to design individual prompts for different tasks and how to modulate their interaction with each other. And this hasn't been explored yet, so having common prompts across tasks. Then, of course, you have the issue with selecting pre-trained models. You have a lot of pre-trained models, and you do without trying, it's really difficult to choose which one you should use. But again, you can choose them on the basis of say your task. So an autoregressive model might be better for prefix prompts and so on. Then you have theoretical and empirical analysis of prompting. Despite the success, theoretical and analysis and guarantees are scarce. So we at all show that soft prompt tuning can relax the non-degeneracy assumptions, like the generation probability of each token is linearly independent, needed for downstream recovery. That is, recover the ground truth labels of the downstream task, making it easier to extract task-specific information. Saunshi et al. Verified that text classification tasks can be reformulated as sentence completion tasks, thus making language model a meaningful pre-training task. Language modeling. Scow and Rush empirically show that prompting is often worth hundreds of points on average across classification tasks. So these are just some analysis, but there is not a lot of analysis. Then you have transferability of prompts. So understanding the extent to which prompts are specific to the model and improving the transferability are also important topics. So would the same prompt which works for GPT-3 work for GPT-2 or GPT-neo? These are some interesting questions. Perez et al. Showed that prompts selected under tuned few-shot learning scenarios, where one has larger validation set to choose prompts, generalize well across models of similar size, while prompts which are chosen in truer few-shot learning scenario do not generalize quite effectively. The transferability is poor when the model sizes are quite different in both scenarios, because then I guess like this is just an introductory explanation, but you might be querying in different spaces in some sense, because your information might be more sparsely located in the model's neurons. So combination of different paradigms. Notably, much of the success of prompting paradigm is built on top of pre-trained models, such as BERT. However, are the pre-training methods that are effective for the latter applicable as is to the former, or can we entirely rethink our pre-training methods to further improve accuracy or ease of applicability to prompt-based learning? So this is one task. A lot of people might not be doing this because, first of all, it's really hard to retrain a model. It's very expensive, very time taking, and it's very hard to justify as well in some sense, because these models are extensively used in other tasks apart from prompt learning. So creating prompt specific models, unless you have very strong guarantees of generalizability, would be very hard to justify. So now, calibration of prompting methods. Calibration refers to the ability of a model uh, to make good probabilistic predictions. So when using the generation probability of pre-trained language model to predict the answer, we need to be careful, since the probability distribution is typically not well calibrated. The Jiang et al. Observed the probabilities of pre-trained models like BAR, T5, GPT-2, and QA tasks are well calibrated. Zhao et al. Identified three pitfalls. So you have a majority label bias, recency bias, and common token bias. So these lead to the most common biases. For example, if the final answer prompt has a positive label, then this will bias the model towards predicting positive words. So this is because this is where your ordering of prompts and choosing right prompts comes into play. To overcome these pitfalls, Java told you first use context-free input. So the prompt would be input, subpar acting, sentiment negative, and then so on to get the initial probability distribution P naught. And then they use a real input example. The prompt would be input subpar acting, sentiment negative, beautiful film, sentiment positive, to get the probability distribution P1. So here you haven't yet given the input in the first case, but you have in the second case. Finally, these two distributions can be used to get a calibrated generation probability distribution. However, this method has two drawbacks. It comes up with the overhead of finding proper context-free prompts like whether to use NA or none, things like that, and the probability distribution of the underlying pre-trained language model is still not calibrated because you're just tuning it on a higher or a more higher level of abstraction, not really tuning the language model itself. Even though we have calibrated probability distributions, we also need to be careful when we assume a single gold answer because there could be multiple answers. For example, if we consider the gold answer to be whirlpool bath, the generation probability of it will typically be low since the word bathtub shares the same meaning and it has occurs more frequently, so it has a larger probability mass. So to address this issue, you can perform answer engineering to construct a comprehensive gold answer set or calibrate the probability of word based on its prior likelihood within the context. So these are just all the challenges which we currently have with prompt-based learning. Next, we go on to some meta-analysis. In this section, we aim to give a quantitative bird's-eye view of existing research by performing a meta-analysis over existing works. So this is a timeline. The time for each paper is when it was posted, and red considers NLU, blue is NLG, and green is both. Okay, so I see a lot of red, so a lot of NLU tasks. Um, right, so the timeline. Okay, so these are just some general things not really related to prompt learning itself, but how it has developed, I guess. So we first summarize the existing papers in chronology. So you have years, you have the tasks which to take on, then you have automatic search. So how many use automatic search for template finding, and then you is your search space continuous or discontinuous. So these are all very interesting to see. You can see like the continuous answer search space only arose in 2021. So tasks, so these are the commonly used tasks, so like text classification, factual probing, and so on. Then you have prompt versus answer. So these, I guess, these plots are very self-explanatory. I won't be going over them. Finally, you have your conclusion. So in this paper, they have summarized extensively. They have mentioned, they have extensively covered all the different things, all the challenges, all the different methods already existing and the challenges associated with them. So I guess we don't really need to read the conclusion if we've read the work so far. And I hope this inspires you to do some work. This certainly inspires me to do some work. And this has probably been the longest paper I've ever covered on my channel. This is already the fourth part, and this video already is around 25 minutes long. So I'm just thinking I'll just upload this as a fourth part, and then for people who might be interested in finding one video covering the whole paper, I'll create all of them combined into one video. So these are just the language models and their sizes and so on. So thank you guys for tuning in. Hope to see you again in future videos as well.